Diamond is a metastable allotrope of carbon, where the carbon atoms are arranged in a variation of the face-centered cubic crystal structure called a diamond lattice. Diamond is less stable than graphite, but the conversion rate from diamond to graphite is negligible at standard conditions. Diamond is renowned as a material with superlative physical qualities, most of which originate from the strong covalent bonding between its atoms. In particular, diamond has the highest hardness and thermal conductivity of any bulk material. Those properties determine the major industrial application of diamond in cutting and polishing tools and the scientific applications in diamond knives and diamond anvil cells. Because of its extremely rigid lattice, it can be contaminated by very few types of impurities, such as boron and nitrogen. Small amounts of defects or impurities color diamond blue, yellow, brown, green, purple, pink, orange or red. Diamond also has relatively high optical dispersion. Most natural diamonds are formed at high temperature and pressure at depths of 140 to 190 kilometers in the Earth's mantle. Carbon-containing minerals provide the carbon source, and the growth occurs over periods from 1 billion to 3.3 billion years. Diamonds have brought close to the Earth's surface through deep volcanic eruptions by magma, which cools into igneous rocks known as kimberlites and lamproites. Diamonds can also be produced synthetically in AHPHT method, which approximately simulates the conditions in the Earth's mantle. An alternative and completely different growth technique is chemical vapor deposition. Several non-diamond materials, which include cubic zirconia and silicon carbide and are often called diamond simulants, resemble diamond in appearance and many properties. Special gemological techniques have been developed to distinguish natural diamonds, synthetic diamonds, and diamond simulants. The word is from the ancient Greek delta alpha mu alpha sigma adamas, unbreakable. History. The name diamond is derived from the ancient Greek alpha delta alpha mu alpha sigma proper, unalterable, unbreakable, and tamed, from un plus delta alpha mu alpha omega, I overpower, I tame. Diamonds are thought to have been first recognized and mined in India, where significant alluvial deposits of the stone could be found many centuries ago along the rivers Penna, Krishna and Godavari. Diamonds have been known in India for at least 3,000 years, but most likely 6,000 years. Diamonds have been treasured as gemstones since the use as religious icons in ancient India. The usage in engraving tools also dates to early human history. The popularity of diamonds has risen since the 19th century because of increased supply, improved cutting and polishing techniques, growth in the world economy, and innovative and successful advertising campaigns. In 1772, Antoine Lavoisier used a lens to concentrate the rays of the sun on a diamond in an atmosphere of oxygen, and showed that the only product of the combustion was carbon dioxide, proving that diamond is composed of carbon. Later in 1797, Smiths and Tennant repeated and expanded the experiment by demonstrating that burning diamond and graphite releases the same amount of gas. He established the chemical equivalence of these substances. The most familiar uses of diamonds today are as gemstones used for adornment, a use which dates back into antiquity, and as industrial abrasives for cutting hard materials. The dispersion of white light into spectral colors is the primary gemological characteristic of gem diamonds. In the 20th century, experts in gemology developed methods of grading diamonds and other gemstones based on the characteristics most important to the value as a gem. 4 characteristics, known informally as the 4 C's, are now commonly used as the basic descriptors of diamonds. These are carat cut, color, and clarity. A large, flawless diamond is known as a paragon. Natural history. The formation of natural diamond requires very specific conditions. Exposure of carbon-bearing materials to high pressure, ranging approximately between 45 and 60 kilobars, but at comparatively low temperature range between approximately 900 and 1300 degrees Celsius. These conditions are met in two places on Earth: in the lithospheric mantle below relatively stable continental plates, and at the site of a meteorite strike. Formation in cratons. The conditions for diamond formation to happen in the lithospheric mantle occur at considerable depth corresponding to the requirements of temperature and pressure. These depths are estimated between 140 and 190 kilometers, though occasionally diamonds have crystallized at depths about 300 kilometers. The rate at which temperature changes with increasing depth into the Earth varies greatly in different parts of the Earth. In particular, under oceanic plates, the temperature rises more quickly with depth, beyond the range required for diamond formation at the depth required. The correct combination of temperature and pressure is only found in the thick, ancient, and stable parts of continental plates where regions of lithosphere known as craton's exist. Long residence in the cratonic lithosphere allows diamond crystals to grow larger. Through studies of carbon isotope ratios, it has been shown that the carbon found in diamonds comes from both inorganic and organic sources. Some diamonds, known as hardsbergitic, are formed from inorganic carbon originally found deep in the Earth's mantle. In contrast, eclogitic diamonds contain organic carbon from organic detritus that has been pushed down from the surface of the Earth's crust through subduction, before transforming into diamond. These two different sources of carbon have measurably different 13C/12C ratios. Diamonds that have come to the Earth's surface are generally quite old, ranging from under 1 billion to 3.3 billion years old. This is 22% to 73% of the age of the Earth. Diamonds occur most often as euhedral, rounded octahedra, and twinned octahedra are known as macles. As diamonds' crystal structure has a cubic arrangement of the atoms, they have many facets that belong to a cube: octahedron, rhombicose, dodecahedron, tetrachys, hexahedron, and distiachys, dodecahedron. The crystals can have rounded off and unexpressive edges and can be elongated. Sometimes they are found grown together or form double-twinned crystals at the surfaces of the octahedron. These different shapes and habits of some diamonds result from differing external circumstances. Diamonds are commonly found coated in NYF, an opaque gum-like skin. Transport from mantle. Diamond-bearing rock is carried from the mantle to the Earth's surface by deep origin volcanic eruptions. The magma for such a volcano must originate at a depth where diamonds can be formed, 150 kilometers or more. This is a relatively rare occurrence. These typically small surface volcanic craters extend downward in formations known as volcanic pipes. The pipes contain material that was transported toward the surface by volcanic action, but was not ejected before the volcanic activity ceased. During eruption, these pipes are open to the surface, resulting in open circulation. Many xenoliths of surface rock and even wooden fossils are found in volcanic pipes. Diamond-bearing volcanic pipes are closely related to the oldest, coolest regions of continental crust. This is because cratons are very thick, and the lithospheric mantle extends to great enough depth that diamonds are stable. Not all pipes contain diamonds, and even fewer contain enough diamonds to make mining economically viable. The magma in volcanic pipes is usually one of two characteristic types which cool into igneous rock known as either kimberlite or lamproite. The magma itself does not contain diamond. Instead, it acts as an elevator that carries deep-formed rocks, minerals, and fluids upward. These rocks are characteristically rich in magnesium-bearing olivine, pyroxene, and amphibole minerals, which are often altered to serpentine by heat and fluids during and after eruption. Certain indicator minerals typically occur within diamantiferous kimberlites and are used as mineralogical traces by prospectors, who follow the indicator trail back to the volcanic pipe, which may contain diamonds. These minerals are rich in chromium and titanium, elements which impart bright colors to the minerals. The most common indicator minerals are chromium garnets, eclogitic garnets, orange titanium pyrope, red high chromium spinels, dark chromite, bright green chromium diopside, glassy green olivine, black picroilmenite, and magnetite. Kimberlite deposits are known as blue ground for the deeper serpentinized part of the deposits, or as yellow ground for the near-surface smectite clay and carbonate weathered and oxidized portion. Once diamonds have been transported to the surface by magma in a volcanic pipe, they may erode out and be distributed over a large area. A volcanic pipe containing diamonds is known as a primary source of diamonds. Secondary sources of diamonds include all areas where a significant number of diamonds have been eroded out of the kimberlite or lamproid matrix, and accumulated because of water or wind action. These include alluvial deposits and deposits along existing and ancient shorelines, where loose diamonds tend to accumulate because of the size and density. Diamonds have also rarely been found in deposits left behind by glaciers, in contrast to alluvial deposits. Glacial deposits are minor and therefore not viable commercial sources of diamond. Space diamonds. Not all diamonds found on Earth originated on Earth. Primitive interstellar meteorites were found to contain carbon, possibly in the form of diamond. A type of diamond called carbonado that is found in South America and Africa may have been deposited there via an asteroid impact about 3 billion years ago. These diamonds may have formed in the interstellar environment, but as of 2008, there was no scientific consensus on how carbonado diamonds originated. Diamonds can also form under other naturally occurring high-pressure conditions. Very small diamonds of micrometer and nanometer sizes, known as microdiamonds and nanodiamonds respectively, have been found in meteorite impact craters. Such impact events create shock zones of high pressure and temperature suitable for diamond formation. Impact-type microdiamonds can be used as an indicator of ancient impact craters. Popigai crater in Russia may have the world's largest diamond deposit, estimated at trillions of carats, and formed by an asteroid impact. Scientific evidence indicates that white dwarf stars have a core of crystallized carbon and oxygen nuclei. The largest of these, found in the universe so far, BPM 37093, is located 50 light-years away in the constellation Centaurus. A news release from the Harvard-Smithsonian Center for Astrophysics described the 2,500-mile-wide stellar core as a diamond. Material properties. A diamond is a transparent crystal of tetrahedrally bonded carbon atoms in a covalent network lattice that crystallizes into the diamond lattice, which is a variation of the face-centered cubic structure. Diamonds have been adapted for many uses because of the material's exceptional physical characteristics. Most notable are its extreme hardness and thermal conductivity, as well as wide band gap and high optical dispersion. above 7 quintillion 3 quadrillion 197 trillion 315 billion spadesuit 1700 degrees Celsius in vacuum or oxygen-free atmosphere. Diamond converts to graphite in air. Transformation starts at tilde 7 quintillion 2 quadrillion 973 trillion 150 billion spadesuit 700 degrees Celsius. Diamond's ignition point is 720-7031073150000 spadesuit 800 degrees Celsius in oxygen and 850-7031273150000 spadesuit 1000 degrees Celsius in air. Naturally occurring diamonds have a density ranging from 3.15-7 quintillion 3 quadrillion 353 trillion spadesuit 3.53 grams per cc, with pure diamond close to 7 quintillion 3 quadrillion 352 trillion spadesuit 3.52 grams per cc. The chemical bonds that hold the carbon atoms in diamonds together are weaker than those in graphite. In diamonds, the bonds form an inflexible three-dimensional lattice, whereas in graphite, the atoms are tightly bonded into sheets, which can slide easily over one another, making the overall structure weaker. In a diamond, each carbon atom is surrounded by neighboring four carbon atoms forming the tetrahedral-shaped unit. Hardness. Diamond is the hardest known natural material on both the Vickers and the Mohs scale. Diamond's hardness has been known since antiquity, and is the source of its name. Diamond hardness depends on its purity, crystalline perfection and orientation. Hardness is higher for flawless, pure crystals oriented to the NLT 111 and GT direction. Therefore, whereas it might be possible to scratch some diamonds with other materials, such as boron nitride, the hardest diamonds can only be scratched by other diamonds and nanocrystalline diamond aggregates. The hardness of diamond contributes to its suitability as a gemstone. Because it can only be scratched by other diamonds, it maintains its polish extremely well. Unlike many other gems, it is well suited to daily wear because of its resistance to scratching, perhaps contributing to its popularity as the preferred gem in engagement or wedding rings, which are often worn every day. The hardest natural diamonds mostly originate from the Copeton and Bingara fields located in the New England area in New South Wales, Australia. These diamonds are generally small, perfect to semi-perfect octahedra and are used to polish other diamonds. The hardness is associated with the crystal growth form, which is single-stage crystal growth. Most other diamonds show more evidence of multiple growth stages, which produce inclusions, flaws, and defect planes in the crystal lattice, all of which affect the hardness. It is possible to treat regular diamonds under a combination of high pressure and high temperature to produce diamonds that are harder than the diamonds used in hardness gauges. Somewhat related to hardness is another mechanical property, toughness, which is a material's ability to resist breakage from forceful impact. The toughness of natural diamond has been measured as 7.5 to 10 megapascals m1/2. This value is good compared to other ceramic materials, but poor compared to most engineering materials such as engineering alloys, which typically exhibit toughnesses over 100 megapascals m1/2. As with any material, the macroscopic geometry of a diamond contributes to its resistance to breakage. Diamond has a cleavage plane and is therefore more fragile in some orientations than others. Diamond cutters use this attribute to cleave some stones prior to faceting. Impact toughness is one of the main indexes to measure the quality of synthetic industrial diamonds. pressure resistance, used in so-called diamond anvil experiments to create high-pressure environments. Diamonds are able to withstand crushing pressures in excess of 600 gigapascals. Electrical conductivity. Other specialized applications also exist or are being developed, including use as semiconductors. Some blue diamonds are natural semiconductors, in contrast to most diamonds, which are excellent electrical insulators. The conductivity and blue color originate from boron impurity. Boron substitutes for carbon atoms in the diamond lattice, donating a hole into the valence band. Substantial conductivity is commonly observed in nominally undoped diamond grown by chemical vapor deposition. This conductivity is associated with hydrogen-related species adsorbed at the surface, and it can be removed by annealing or other surface treatments. Surface property. Diamonds are naturally lipophilic and hydrophobic, which means the diamond surface cannot be wet by water but can be easily wet and stuck by oil. This property can be utilized to extract diamonds using oil when making synthetic diamonds. However, when diamond surfaces are chemically modified with certain ions, they are expected to become so hydrophilic that they can stabilize multiple layers of water ice at human body temperature. The surface of diamonds is partially oxidized. The oxidized surface can be reduced by heat treatment under hydrogen flow. That is to say, this heat treatment partially removes oxygen-containing functional groups, but diamonds are unstable against high temperature under atmospheric pressure. The structure gradually changes into sp2c above this temperature. Thus, diamonds should be reduced under this temperature. Chemical stability. Diamonds are not very reactive. Under room temperature, diamonds do not react with any chemical reagents including strong acids and bases. A diamond surface can only be oxidized at temperatures above about 850 degrees Celsius in air. Diamond also reacts with fluorine gas above about 700 degrees Celsius. Color. Diamond has a wide band gap of 6,881,197,607,849,999 spade suit 5.5 electron volts corresponding to the deep ultraviolet wavelength of 225 nanometers. This means pure diamond should transmit visible light and appear as a clear colorless crystal. Colors in diamond originate from lattice defects and impurities. The diamond crystal lattice is exceptionally strong and only atoms of nitrogen, boron and hydrogen can be introduced into diamond during the growth at significant concentrations. Transition metals nickel and cobalt, which are commonly used for growth of synthetic diamond by high-pressure, high-temperature techniques, have been detected in diamond as individual atoms. The maximum concentration is 0.01% for nickel and even less for cobalt. Virtually any element can be introduced to diamond by ion implantation. Nitrogen is by far the most common impurity found in gem diamonds and is responsible for the yellow and brown color in diamonds. Boron is responsible for the blue color. Color in diamond has two additional sources: irradiation, that causes the color in green diamonds, and plastic deformation of the diamond crystal lattice. Plastic deformation is the cause of color in some brown and perhaps pink and red diamonds. In order of rarity, yellow diamond is followed by brown, colorless, then by blue, green, black, pink, orange, purple, and red, black, or carbonado. Diamonds are not truly black, but rather contain numerous dark inclusions that give the gems their dark appearance. Colored diamonds contain impurities or structural defects that cause the coloration, while pure or nearly pure diamonds are transparent and colorless. Most diamond impurities replace a carbon atom in the crystal lattice, known as a carbon flaw. The most common impurity, nitrogen, causes a slight to intense yellow coloration depending upon the type and concentration of nitrogen present. The Gemological Institute of America classifies low saturation yellow and brown diamonds as diamonds in the normal color range, and applies a grading scale from D to Z. Diamonds of a different color, such as blue, are called fancy-colored diamonds, and fall under a different grading scale. In 2008, the Wittelsbach diamond, a 35.56-carat blue diamond once belonging to the King of Spain, fetched over $24 million at a Christie's auction. In May 2009, a 7.03-carat blue diamond fetched the highest price per carat ever paid for a diamond when it was sold at auction for 10.5 million Swiss francs. That record was however beaten the same year. A 5-carat vivid pink diamond was sold for $10.8 million in Hong Kong on December 1, 2009. Identification diamonds can be identified by the high thermal conductivity. The high refractive index is also indicative, but other materials have similar refractivity. Diamonds cut glass, but this does not positively identify a diamond because other materials, such as quartz, also lie above glass on the Mohs scale and can also cut it. Diamonds can scratch other diamonds, but this can result in damage to one or both stones. Hardness tests are infrequently used in practical gemology because of the potentially destructive nature. The extreme hardness and high value of diamond means that gems are typically polished slowly using painstaking traditional techniques and greater attention to detail than is the case with most other gemstones. These tend to result in extremely flat, highly polished facets with exceptionally sharp facet edges. Diamonds also possess an extremely high refractive index and fairly high dispersion. Taken together, these factors affect the overall appearance of a polished diamond, and most diamanteurs still rely upon skilled use of a loupe to identify diamonds by eye.